In this segment, I'm going to describe various different inter-process communication options that you're going to need when you're developing your microservice-based application. So there are basically two different communication styles that your microservices can use. They could use an asynchronous messaging approach, or they could use a remote procedure invocation, or RPC approach as it's commonly named. So the reason you need to think about this is because unlike in a monolithic application where everything is in one process and all invocations are local language level method calls and function calls, in a microservice architecture, your microservices are invariably separate processes which could very well be running on different machines, and so you need a mechanism to enable communication between these different processes. So one facet to this is actually the different interaction styles that can occur between a pair of processes. And there's actually sort of two different dimensions that you can organize it by. So one dimension is whether it's one-to-one or one-to-many, and then the other dimension is whether it's synchronous versus asynchronous. So one very common interaction style is synchronous one-to-one approach, which is request-reply. So that's typically HTTP. A client makes a request and it waits for a reply. So that's sort of standard HTTP REST that we're very, very familiar with. But then there's various asynchronous communication styles. So there's asynchronous one-to-one. I can just send you a notification and I'm neither going to wait for a response or actually expect one. Or I could send you a request and then at some point in the future, perhaps within milliseconds or perhaps within hours or days, you're going to send me back a response to that. So that's request async response. And then there's also asynchronous one-to-many, where I publish something and that message is consumed by numerous subscribers. And I'm not really aware of who is actually consuming my message. But then there's also asynchronous publish with waiting for one or more responses to come back asynchronously. It's a really interesting alternative approach to gathering the data needed to render a product details page. So rather than making synchronous requests to various backend services over REST, I could instead just publish a message, give me information about this product, and various subscribers could be the product catalog or the catalog service, the review service, the recommendation service. They asynchronously get the message and then just send one back. And I would wait for all of those messages to come back, aggregate them together, and send back a response to the client. So there's a couple of different ways of doing this scatter-gather style of communication. One would be just a whole bunch of request replies, or I could do a publish with asynchronous response. Another thing you need to think about is defining APIs. What's really interesting is if you look back over how sort of remoting technology has evolved, Corba was, from many, many years ago, was all about IDL, interface definition languages. Then you had SOAP, which had WSDL. And then those all fell out of favor. They were determined to be too complex. And we ended up adopting REST with, say, JSON instead of XML as the format for the bodies. What was really interesting is when we did that, we kind of forgot about defining APIs. The APIs tended to be somewhat implicit. But I think the community has since realized that we do need some kind of IDL to unambiguously specify the interfaces between different components. And so in the REST world, folks are starting to adopt technologies like RAML and Swagger You can also use JSON schema for defining the structure of the JSON messages that are passed around over a message broker. And then there are also some binary communication technologies that actually are IDL based, like Thrift and Protocol Buff and Avro and so on. It can actually make sense to use an API first approach to designing your APIs. So you actually specify the API using an IDL, could be Swagger or RAML. Then you can review it with the developers who are going to consume your service, and you can iterate around a few times and then go ahead and implement it. And I think that's very much worth considering, as opposed to sort of informally figuring out what the API is and then using, for instance, a plugin with Swagger to generate the API definition by using reflection on your Java classes, for example. So take a look at using an API first approach to designing your services. There are a bunch of different options with messaging formats. So human readable text is very popular, and JSON, of course, is the fashionable format that people use widely today. And on the one hand, those are actually quite good. They're actually self-descriptive. The actual message format, at least abstractly, consists of name-value pairs. So that lets you evolve your APIs by adding new name-value pairs, and the consumer knows what it's getting. It can actually just ignore the name-value pairs that it doesn't recognize. The downside is that these text formats are somewhat bulky. There's a lot of repetition, and they tend to be slow to parse as well, so there's considerable overhead. Another option to use for messages is actually some kind of binary protocols. They tend to be more compact, they tend to be faster to parse, but not all of them actually are self-descriptive, which can make evolving APIs more challenging. The client actually has to know the schema of the binary message that it's getting. So that can be challenging. So there's very, very interesting trade-offs there. You have to think hard about evolving APIs because change is inevitable. You can actually think of changes falling into one of two categories. You can have minor backwards compatible changes, right, where you're just simply adding new name value pairs to a request or a response. And provided that you design servers to provide defaults for missing values and clients to ignore values that they don't understand, then clients and servers that are sort of older clients can happily interoperate with newer servers, and everything just works fine. Sometimes, however, you actually have to have major changes that are not backwards compatible, and there you want to actually bake version numbers into URLs or MIME types. So there's a lot of issues that you actually have to think about when you're building a distributed system. Now, in terms of just nuts and bolts, right, there's sort of two different sort of technologies or types of technologies that you can use for inter-process communication. So one is to have an asynchronous messaging-based approach, right, which abstractly is a sender of a message writes the message to a messaging channel that's somewhere within a messaging system, and then there's a recipient who reads that message from the channel. In practice, those could be JMS queues or topics, whatever sort of maps to the terminology of your messaging system. So this approach has various benefits. It decouples the clients from the services, so the client can just send a request to the messaging system, and a service can pick that messaging up at some point when it's ready. And if the service is down, the message broker will happily buffer up those messages until the server is ready to consume it. So you get this nice decoupling. And this approach also supports a variety of communication patterns. All of the ones I outlined earlier, asynchronous one-to-one, asynchronous one-to-many, as well as synchronous one-to-one. So the drawbacks of this approach are you actually have to have a messaging broker, which is yet another component of your system that you have to operate, and it has to be highly available. Also, implementing request-reply style communication is a bit more complex over an asynchronous message bus. It's sort of not a natural fit. And then one minor problem is the client needs to discover the location of a message broker, but that tends to be fairly straightforward. There are various examples of messaging systems. ActiveMQ has been used for quite a while. There's RabbitMQ. And then there's a couple of newer ones. There's NSQ, which is getting adoption in some quarters. And then there's also Apache Kafka that's sort of quite popular within Silicon Valley. Initially created at LinkedIn. And they've demonstrated Kafka operating at like this incredibly massive scale. It's very impressive. So that's messaging systems. The other way of implementing IPC is to use some kind of remote procedure invocation or RPC mechanism, which abstractly looks like this, right? A client has some stub code that makes a request to a server that sends back a reply. There's various different implementations of that. Today we use REST, but there's quite a few other sort of technologies that support that style. Now, there's one benefit of this is that it tends to be simple and familiar, right? We're all familiar with HTTP and REST and so on, so that's quite good. It's also direct. The client talks to a service. There's no intermediate broker, so our system is simpler. Downside is that it only supports request reply. That's an inherent part of a protocol like HTTP. Client makes a request, server sends back a reply. Also, it requires the service to be available. So there's sort of this temporal coupling. A client can't send a request unless the server is available to receive it. And another issue, which tends to be quite a big issue, is that the client needs to know the network location of the service instances that it's talking to. And later on, there's a whole series of segments on the problem of service discovery. So as I mentioned, there's a few different remote procedure invocation mechanisms. A very popular one, of course, is REST, that's HTTP based, which is nice. It's firewall friendly. You get to pick the messaging format. Often it's JSON, for instance. There's also Thrift, that's an RPC framework, and you generate client stubs and server skeletons from an IDL, and it supports both binary and JSON message formats, and it can work over raw TCP or HTTP. So you've got a few different options there. So one issue that you have to deal with in a remote procedure invocation application, and in some cases in a messaging-based application, you have to deal with the problem of partial failure. So imagine that you're implementing a web application that's rendering a product details page. You need to make requests to the catalog service, the recommendation service, the review service, and so on. But let's imagine, what do you do if the recommendation service does not respond, right? We try hard to make our services highly available, but sometimes they can just be misbehaving and be really slow, or they could just be down. So you actually have to spend time thinking about it, because one scenario that you really want to avoid is this one. So imagine a request comes in for the product details page. You invoke the recommendation service using some HTTP client code, but the recommendation service doesn't respond. it just doesn't send back an HTTP response. And let's say that your code is written in a way that just means that it's just going to wait. What will happen in a Tomcat environment is that that thread will just be blocked indefinitely. Or at least until the recommendation service responds, which actually could be never, right? So you only have a finite number of threads and you've just blocked one of them. Imagine another request comes in for this, and that calls the recommendation service and blocks. That thread's going to be blocked, and so on and so forth. And say, maybe you have 200 execute threads. 200 requests later, all of your execute threads are busy, and Tomcat is now unable to process any requests. And this could so that Tomcat instance is not working, and this problem could very well quickly happen to your entire system. It just stops working. So what do you do about it? So a good approach is to adopt the strategy that's taken by Netflix. So number one, when one service calls another, you always do it with a timeout. You never block indefinitely. So that means that you're never going to tie up an execute thread for an indefinite period of time. What's more, another thing that you do, you always invoke a remote service by a bounded thread pool. And the reason for doing that is that it actually imposes an upper bound on the number of outstanding requests that, say in this case, the web application can make to the recommendation service. So if you have too many outstanding requests, the thread pool will fill up. And then the queue that's sort of backing that thread pool is going to reach capacity as well. And you're going to start failing fast. So you're not even going to wait for this recommendation service to like not respond to you. You're actually going to fail fast from that point on. So you're not even going to tie up any threads. So that's a big improvement. And then there's another thing you can do, which actually which is incredibly useful. You actually monitor the error rate when invoking a remote service using the circuit breaker pattern. And so what happens is that, say, let's imagine that you see 5 failures in a row. That could be a great indication that the service you're trying to invoke is unavailable. So what you do is trip the circuit breaker, and from that point on, any attempt to make a request to that remote service fails immediately. And then, after a certain timeout period, the circuit breaker closes again and starts allowing requests through. And if it succeeds, then everything's back to normal. Otherwise, it stays open and for another timeout period. So you get this fail fast. If there's a serious problem, a long-term problem with some remote service, then you actually stop trying to invoke it and wait, and you just fail fast instead. So that makes your system more robust against failure in other services. So then the issue you have to deal with is, what do you do if that remote service is unavailable? So in this case, if the recommendation service is unavailable. So one thing you could do is return default data back to the client. So, rather than showing recommendations, maybe you're just going to show the popular movies of today, right? That's better than showing nothing. You could actually just sort of display no recommendations, right? That would be pretty good as well. You want to try and avoid returning an error to the caller, but sometimes that's exactly what you need to do. And maybe in the case of Netflix, that an error gets returned to their client, which can then repeat the request and then get load balanced to a different part of the cluster that's fully working, and your kids get to watch their cartoons. Netflix actually have an open source library called Hystrix that implements a lot of this functionality. So it implements the circuit breaker pattern and the error handling capability. And if you're building a system in Java, it's well worth taking a look at Hystrix. So anyway, that was a sort of brief overview of inter-process communication issues. We looked at interaction styles, we looked at messaging versus RPC, and we spent some time looking at partial failure. In the next section, we're going to start looking at the issue of service discovery.